Today's lesson is going to be on higher order derivatives. This is essentially when we take the derivative of the derivative. As we know, the first derivative tells us the slope of a function, and this essentially tells us if the graph is going up or if it's going down. Now the second derivative, which is the derivative of the derivative, this isn't going to tell us the slope of the graph. This is going to tell us something called the concavity of the graph. And concavity is a little bit of a weirder concept. It's essentially the shape of the graph. So there's two main things that could happen. The first is if your second derivative is positive, then your graph is going to be concave up. And essentially what this means is the slope of the derivative is increasing. So if the slope starts off near 0, that slope's going to be getting bigger and bigger and bigger. This means it's going to be getting steeper and steeper. And on the other hand, if you had a graph that had a negative slope, but it was concave up, as the slope gets bigger, the number is going to get less and less negative and closer to 0, which means as the function decreases, if it's concave up, it's actually going to get shallower. And then once it hits 0, then it starts getting bigger. This means if the graph is concave up, it's going to be U-shaped. The way you can think of it, concave up has the U in it, so that's going to make a U shape. The other end is if the second derivative is negative, that's going to make the graph concave down. And you might be able to guess the shape of a concave down graph, but essentially it's going to be the opposite. It's going to be an N-shaped graph. Another way you can remember this is a concave down graph makes a frowny face for down. Concave up, smiley face. We're going to be getting more into these concepts in future lessons. Today's focus is going to be more on the notation and taking the second derivative itself. There's a couple of notational ways to write the second derivative. One way is to do it with two apostrophes. So instead of f prime of x, it's f double prime of x, or f apostrophe apostrophe of x. Additionally, you can also see it in the dy dx notation, and they write a little funny. They generally do d2 y over dx 2. So that's d squared y over dx squared. And essentially, in calculus, d over dx is a function almost. So d over dx means take the derivative of whatever comes next. So this means take the derivative of the function y. And you could slip that y into the top. So generally, this is how we write the first derivative. The reason we don't put the exponent on the end is because we don't want to square the y function. Instead, we want to do this derivative function twice. So instead of d over dx y squared, it's d over dx. We essentially square it or write it as a square to show we want to do this function twice. And we can distribute that square to both the top and the bottom. And then when we slide the y to the top, that's why you get this funny notation where the exponents kind of feel off-center. But in general, don't overthink the notation. Another thing, though, is you can see higher order derivatives. So this is the second derivative. You can also see third derivatives or fourth derivatives. You might see one down here in problem number 4. You can also write it in this f notation by doing f, and then in parentheses, whatever derivative you want. So f4 in parentheses of x would mean the fourth derivative of x. All right, so let's do a problem. Find the second derivative of f of x equals x to the fourth. To take the first derivative, this is just going to be power rule. So we're going to move that exponent to the front, and that's going to become 4x cubed. So now in order to get the second derivative, we have to take the derivative of this derivative. So once again, we're going to be using power rule. So the derivative of 4x cubed, that's going to be 12x squared. We move that 3 to the front. 3 times 4 is 12. Take 1 away from 3, you get x squared. And this is just going to be our final answer. Now for number 2, it's going to be a similar problem, just a little bit more going on. The first derivative we can also write as y prime. It's just going to be power rule. 3x squared becomes 6x, minus 5x becomes minus 5. That constant is a derivative of 0, so it's just going to go away. But now this question is asking for the second derivative. So I'm going to change up our notation here to get it to match. The second derivative of y is going to be the derivative of this derivative, which is just 6. Now the third problem, for f of x equals 3 sine of x, find the second derivative of f. Well, the first derivative, we have a constant in front, but the derivative of sine is positive cosine. Now to get the second derivative, we take the derivative of this function. Remember, cosine, it starts off decreasing, so the derivative of cosine is negative sine. So this derivative is negative 3 sine of x, and that's going to be our second derivative. Now for the fourth one, similar type of problem, but this one is a little tricky. It gives us the first derivative already. This means we want to take the third derivative. We don't want to do the derivative 3 times. We only want to do it 2 more times because we're already at derivative number 1. So the second derivative is just the derivative of what they gave us. That's going to be negative 2 sine of x. And now the third derivative, that's going to be this derivative. That's going to be the derivative of that second derivative. The derivative of sine is positive, so this is going to stay negative. So it's going to be negative 2 cosine of x.